Swayam Prabha. Digital India. Educated India.
Welcome. So, in the last lecture we have seen that how we can find out the seepage through an earthen dam, and there we have established this equation, that is rate of seepage is given by k into L into tan alpha sin alpha, where alpha is nothing but the slope of the downstream phase, that is given by this figure, and k is the coefficient of permeability, whereas L is completely unknown to me, as I told you in the last lecture that L is not known to me. So, I need to find out L. Now, again, so the rate of seepage per unit length of dam through the section BF, any section, say any section in between, say that is BF, okay, along that section, if you say, if I want to find out the rate of seepage, that is given by same k q equal to k into I into A. So, what is I? I is nothing but dz dx. Now, what is the area, cross sectional area at section BF is nothing but z into 1, that 1 is nothing but the unit length normal to the plane, right. So, z is the depth of section BF. So, I can get the expression kz into dz dx. So, that is the rate of seepage at any section BF, okay, which is say some distance away from point D. Okay. So, now this for continuous flow, I mean if you want to satisfy the equation of continuity, right, for the continuous flow, whatever flow is happening through this section BF, the same amount of flow will be happening the section through the section CE. There is no issue, because whatever flow is entering the section BF, the same amount of flow or same amount of seepage will be going out from through section CE. So, I know the rate of seepage through CE, that is nothing but KL tan alpha sin alpha. Do you remember that in the last lecture as well as today already we have seen that. So, KL sin tan alpha sin alpha is the rate of seepage through section CE, whereas along or the across the section BF the rate of seepage is kz into dz dx. So, they must be equal for the continuous flow. Now, we are taking the integration, or we were doing the integration, and the limit is L sin alpha, that is here from this point, because x is varying from section CE to BF, x is varying from L sin alpha to z is varying from L sin alpha to h, because you are considering the whole thing. So, now you are considering from A prime to C. Okay. I hope that you are understanding this thing, right. So, this is my starting point, right. I can go by following this, I can go up to point A prime, right. So, the limit should be, the integration limit should be L sin alpha to h, this is nothing but h, okay, kz dz equal to L cos alpha, that is x is nothing but L cos alpha. So, this is your L cos alpha to d is given here. You see, this is the distance from the point D, small d, to the point A prime, okay, along the x axis. So, if you do the integration, if you perform the integration, you will be getting the expression for L. L is given by this. Okay. So, once you know L, you can find out the rate of seepage through the dam body. Okay. Now, following are the steps to calculate Q. So, whatever we have discussed so far, now we will be talking about those steps in brief. Okay. So, first you obtain alpha. What is alpha? Alpha is nothing but the slope of the downstream surface or the downstream slope, okay, the inclination of the downstream slope. First you obtain alpha, okay. Then you calculate capital delta. What is delta? So, if you see the figure, the delta is nothing but the distance between this point and actual entry point of water, that is A, okay, that is my delta. Okay. So, and you also calculate 0.3 delta to get a point A prime, okay, as I told you. So, that is located at 0.3 delta distance from the actual entry point A. Then you calculate D. How you can calculate D? So, you know this point because the dam geometry is known to you, you know this point. Now, this A point is fixed. So, you can find out the distance between these 2 points. So, small d is known to you now. Now, from alpha and small d, calculate L from equation 2.27 whatever I just discussed. Okay. So, you find out L. Once you know the magnitude of L, then from L basically you calculate small q from equation 2.25, that is K L tan, if you recall, K L tan alpha sin alpha. So, these are the steps involved to obtain the seepage through earthen dam. Now, basically as I told you that we assume that I is equal to dz dx, right. So, sometimes this assumption basically is not serving well for the steeper slope. So, basically Casagrande has proposed some modification in this assumption. So, equation 2.27 is derived on the basis of Duppert's assumption, that is I approximately equal to dz dx, right. Already we have seen that, already we have derived based on that. Now, it was shown by Casagrande that when the downstream slope angle, that is alpha, becomes greater than 30 degree, that means when the downstream slope is becoming little bit steeper, then the deviation from Duppert's assumption become more noticeable. That means, as I told you that if your slope is flatter, that is a downstream slope, the downstream slope is flatter, then this assumption I is approximately equal to dz dx will hold good. But if you go for the steeper slope, then this assumption will not be predicting the things properly. Then at that time you will be getting more deviation from the actual solution and the actual and the theoretical solution, right. So, then Casagrande proposed that you have to modify this assumption little bit. How you can modify? So, the modification is suggested by Casagrande, and he suggested that I should be equal to dz ds. Okay. So, now instead of taking dz dx, you are taking dz ds. What is S? S is nothing but the surface or the parabolic or the phreatic line surface. Okay. So, that ds dz by ds is nothing but equal to sin alpha. If you go back to the previous figure, you will see that dz by ds is nothing but sin alpha. So, where ds is nothing but dx square plus dz square to the power half, that is root over dx square plus dz square. Okay. This is now what I mean to say, in Duppert's proposed that the hydraulic gradient, okay, should be equal to dz dx, where dz is the vertical length and the dx was the horizontal length. Now, instead of taking dz dx, you are considering dz ds, where ds is the actual curve length, okay, that parabolic curve or the phreatic line curve. Now, equation 2.25 then becomes, then k, that will be remaining same, k I a, q equal to k I a is equal to k sin alpha L sin alpha is equal to k L sin square alpha. So, if you go back to equation 2.25, you will see that now your basically I is sin alpha, right. So, you can multiply k with, so I, that is nothing but sin alpha in this case, earlier it was tan alpha, right. Do you remember that? Earlier it was tan alpha, now it is sin alpha, and of course, L